In this video, we're going to explain what the quotient rule is, why it works, how to use it, and if you stick around until the end, why you don't actually need to remember it. So to start, go ahead and pause the video and see if you remember what the quotient rule is. If you already feel like you can remember the quotient rule with no effort, go ahead and skip the video. But if you want to understand it deeper, be sure to stick around. So first off, let's start with what exactly the quotient rule is and when to use it. The quotient rule applies anytime you want to take the derivative of a quotient, hence the name quotient rule. You call whatever is in the numerator f of x and whatever is in the denominator g of x. And then basically, if you know what the derivative of f of x and g of x are individually, you can use this rule to take the derivative of one divided by the other. So let's show an example. So here we're assuming we already know how to take the derivative of sine of x and x squared, which again, those are two separate derivative rules that you would need to know to even begin a problem like this. But assuming you know how to take them individually, we can then use the quotient rule to take the derivative of the quotient of them. So how would you do something like this? If you're not sure, when over time you'll become a lot more comfortable, I think, with the quotient rule to the point where you can do most of this in your head. But if you're just starting out, one thing that's really helpful is to get crystal clear on what is f, what is g, what is f prime, what is g prime, and then just blindly plug them in. That's my advice. So to start, let's write that down. So according to this, what would f of x be? So what's f of x? It's the thing in the numerator, and that is important, by the way. You can't, with the quotient rule, you can't swap f of x and g of x. You can actually get away with that in the product rule if you swap f of x and g of x because it's symmetrical. This one is not symmetrical. If you mix up f and g, you will get it wrong. So you have to be very, very careful about which one's which. But basically, if you look at this, just kind of we're pattern matching here. Whatever's in the numerator, that's f of x, or that's what we call f of x. So that's going to be sine of x. And then whatever is in the denominator is what we call g of x. So that'll be g of x squared. And then you can see in the formula, we're going to need f of x in some places, g of x in some places, but we're also going to need two other things, f prime of x and g prime of x. In other words, the derivatives of their individual functions. What are those? And again, this is where you need to know separate derivative rules. I won't go over those here, but basically the derivative of sine is cosine, and the derivative of x squared is 2x. So if you know those, you're good to go. And then now what we can do is we can just basically blindly plug in. So let's make a little bit of room to do that. So this whole thing is apparently going to equal f prime of x. What did we say that is? Cosine of x. So that's going to be cosine of x times g of x, which is x squared apparently, minus f of x, which is apparently sine of x, times g prime of x, which is 2x. So times 2x, and then divided by the whole thing over g of x squared. So that'd be like x squared squared, the whole thing squared. So there you go. That's the answer. Now, what you might want to do in a problem like this is do a little bit of simplification. So I'll do that. Generally, you want to put polynomials if you can before like trig functions and exponentials. So I'll just rearrange that a little bit. And you also, in general, you want to put constants out front. So I'll say minus 2x sine of x. And then you can use exponent properties to say basically x to the fourth. So that's definitely simpler. Still the same thing, just simpler. And then you could argue, if you notice this, you can see that there's actually a common factor in the numerator of 1x. So if I factor out 1x, I'll be left with x times cosine of x minus 2 times sine of x. And then I can divide the whole thing by x to the fourth. And then one of the x's basically in the numerator and denominator cancel out. So you can basically be left with final answer in the most simplified form that I can see at least. X cosine of x minus 2 sine of x over x cubed. And that apparently is the derivative of sine of x over x squared that we started with at the beginning. So there you go. That's the derivative of sine of x over x squared. But a deeper question is, why does that rule work at all? So here, let's dive into the derivation of the quotient rule. And if you understand this, you technically won't even have to remember the quotient rule. I know the quotient rule is kind of annoying to remember. It's more annoying than the other derivative rules for sure. But if you understand this process, you actually don't need to remember it. You always have a backup plan so that you can rederive it on the fly. So here we go. Let's jump into that. The first thing to understand is that the quotient rule is basically a combination of some other derivative rules, specifically the product rule, the power rule, and the chain rule. This is how you can look at things through that lens. So instead of looking at it as some function f of x divided by g of x, instead look at things like this. And this is kind of the initial setup you need. Look at it as f of x, some function f of x, times some function g of x to the negative first power. So we're basically using a little bit of trickery with negative exponents here. So instead of dividing by some function g of x, you can look at it as multiplying by g of x to the negative 1 power. And then we can go from here. So now if you look at this, you can look at this whole thing as a product rule, if that makes sense. So like f of x times g of x to the negative 1. Now again, I won't go over the product rule. I've covered that in a separate video. But how would we do that? Basically, the derivative of the first, which would just be f prime of x, leave the second. So actually, I'll try to do these in as many parentheses as I can. More parentheses usually help. So g of x to the negative 1. So derivative of the first thing, f prime, leave the second, and then plus leave the first thing, f of x, derivative of the second. So what would that be? That would be negative 1 times g of x to the negative 2. That's the power rule. Bring the power down. So I'm going to use the power rule and the chain rule here. So take the current power, multiply it out front, then decrease by 1. That's what we've done here. And then because this is a chain rule, we need to take the derivative of the inside 2, which would be g prime of x. So there you go. This is the quotient rule, although it really doesn't look like it. So how can we simplify it a little bit more? Well, think about what this is. So this is really f prime of x. And then what does it mean to have g of x to the negative 1 power? It really just means divide by g of x. And then we have a negative 1 here. So we have a negative and then an f of x. And then we have a g prime of x. And then we have g of x to the negative 2 power. That's really going to be g of x squared. And then now, this is a lot cleaner or closer to the final quotient rule. In order to, basically what you need to do here is get a common denominator. So you can basically do g of x over g of x. We're kind of cleverly multiplying by 1 here to not change this term. But yeah, after you do that, hopefully it's clear now that we get to the final version of the quotient rule, which is basically f prime of x times g of x minus f of x times g prime of x all over g of x squared, which is the quotient rule. So again, if you understand that process, you don't need to remember the quotient rule necessarily. It really is just a combination of the other rules, but the combination is a little bit complicated. So honestly, for speed, it still makes sense to remember the quotient rule. So there you go. That's what the quotient rule is, how to use it, and why it's true. Hopefully that makes sense, and I will catch you next time. See you.